All right, so in this module, we're going to talk about extrinsic semiconductors, so the middle one here. All right, so extrinsic semiconductors. So we're talking about adding in things, either intentionally, if we call them dopants, or unintentionally, if they're impurities. And these external things will induce electronic defects like the ones we saw in intrinsic. So it's in this case, it's whatever we're adding, the external factor that we're adding to this. And so just to give you sort of an illustration of this, let's look at silicon. So this is widely used as a semiconductor material for computers and really all electronics. And so I've highlighted that here. And then we're going to look at doping it with different materials to either create free electrons or free electron holes. All right, so the first example I want to look at is the case where we have silicon, but then we dope it with something like phosphorus, P, which is known as a group 5 element. So if I go back to the previous slide, this is the group 5. So it's phosphorus, it could be nitrogen, arsenic. So it's basically to the right of silicon. All right. So if we think about the sort of the structure of silicon, and we think of those as ions, right? Then each silicon is going to be +4. But if we dope in phosphorus, phosphorus has 5 electrons in its outer shell, right? So basically looking at our valence electron. So we have one more electron in the valence shell for phosphorus as opposed to silicon. And so what this does, it leaves one dangling electron in that structure. So because we have a plus structure, then that basically gives us one dangling or additional electron in the structure. So we've kind of added one here to represent that in the schematic. All right, so this extra electron is in what we call a donor level. So kind of illustrated here on an energy plot between the valence and the conduction band. So basically that electron exists at a level higher than the valence band. And so that level is closer to the conduction band. So basically it is more weakly attached to the valence band, and so it's easier to promote that electron to the conduction band. So typically this small amount of energy is readily available at any temperature, and so we can think of that as a free electron because it's already been promoted to the conduction band. So it's either already in the conduction band or can be easily promoted to the conduction band. And so the result of this is that one atom of phosphorus donates one electron to the conduction band, and so it increases the electronic conductivity of silicon and makes it a N-type semiconductor. So it donates electrons, free electrons, and so we've been using the terminology N for electrons. So we call this an N-type semiconductor. All right, so let's look at a different case. So going back to the periodic table here, silicon, and then now let's imagine that we look at a group 3 element. So something like boron B. So now the addition of boron, which replaces silicon, so silicon had 4 valence electrons, now boron, because of its position on the periodic table, only has 3 valence electrons. And so if we're thinking about that in this structure, what this does is it leaves behind an electron hole from the absence of that 4th valence electron. And so in this case, the addition of boron would leave a electron hole in this doped structure. And so that's creating a hole. So one boron would cause one boron would result in the addition of one electron hole. And so this is present at what we call an acceptor level, which is above the valence structure. And so when we apply an electric field in this case, that hole is basically a vacancy in which a neighboring electron can jump. And so that allows electrons in the valence band to easily hop between different sites using that acceptor level, because that is, again, the energy difference here is less than the overall band gap between the valence and conduction band. So that energy is EA, whereas the donor level for the N-type was ED. And so in this case, since we're producing holes, and we've used the terminology P for holes, we call this a P-type semiconductor, one that creates electron holes. So this is a P-type semiconductor. All right, so while we're on the topic of extrinsic semiconductors, I also wanted to talk about some other effects of doping, so external factors, when it comes to conductivity. And so when we looked at various types of defect reactions, and that we saw that sometimes we can balance those reactions by creating various defects. So for example, if we dope in calcium oxide to, the opposite. If we dope in zirconium oxide, ZrO2, into calcium oxide, this, I apologize, I've flipped it a couple times now. We are doping in the calcium oxide into the zirconium structure. And so there you see that calcium into the zirconium sites creates a -2 charge. And to balance that, we can create oxygen vacancies and then one more oxygen that goes into a regular oxygen site. So this is what happens when we dope in calcium oxide into zirconium oxide. And so every time we dope 1 mole of calcium oxide, we create 1 mole of oxygen vacancies. And so when we're looking at conductivity, in this case, ionic conductivity, right? So if we're thinking about the mobility of, for example, oxygen, oxygen is going to hop through these oxygen vacancies. And so we can look at the effect of doping, right? And so based on this, we would expect that the more vacancies we have, the higher the concentration of the species in that conductivity equation is going to be. And so the more calcium we add in or dope, the higher the concentration. And so we'd think the higher the conductivity of the species. And that's what happens initially, right? So down here is the number of anionic vacancies, so oxygen vacancies, as a function of the log of the conductivity. And all of these plots for various materials, various types of doping, we see that the conductivity increases for all of them. But the other part of this is that at a certain point in each of these curves, we reach a max. And beyond that, the conductivity actually goes down, right? So if we're just thinking of the conductivity based on the number of concentration, the concentration level from the equation, we would think that it should keep going up. But this is only true for dilute concentrations. When we get a large enough amount, we have defect interactions with each other. The defects start to interact with each other. So these oxygen vacancies would end up interacting with each other, and that causes the effect on oxygen content. So there's basically a breakdown of that equation when it's no longer dilute. So that's just one other factor that can affect extrinsic conductors, in this case ionic conductors.